Welcome back, everyone. This is Try-Catch Plan, and I'm your Try-Catch engineer, Glenn. This time I'm going to wire up some LEDs to provide visual feedback and animation to go along with the sound files that our little media app is playing. So first up, I'll get the green, yellow, and red LEDs on the breadboard. According to their datasheet, my LEDs have an average forward voltage of 2.2, 2.1, and 2.0 volts operating at 20 milliamps. That means the LEDs consume that much of the input voltage, so I need resistors, 1 to consume the rest, and 2 to limit the current. With 3.3 volt pins, that means I need resistors for 1.1, 1.2, and 1.3 volts at 20 milliamps. Since V equals IR, aka V over I equals R, we get 55, 60, and 65 ohms. Power equals current times voltage, which means we're working with 20 or so milliwatts, so a 250 milliwatt resistor will be up to the job and have enough factor of safety to stay cool and not blow up. And Google around for how gpiozero handles multiple LEDs as a group. They have a class called LED board, which is what I'll use. Okay, so the first interesting problem was running the LEDs and sound at the same time. That should be doable with threads, so I looked up a simple way to run a lambda function separately of my main application. Google Python thread timer lambda, and that'll get you there. That works great, but next I wanted a sequence of any combinations of 1, 2, or all 3 LEDs lighting, so I created a simple array of dictionaries containing the desired LED values and the duration for that state, and sent that off to my function. And that gets us to the second interesting problem. The way I'm creating timers, they all get created at once, so I need each timer to run after the previous one. So for now, I just ended up summing all the durations as I go. The third gotcha here is to deal with the default pass-by reference in a lambda execution. Python knows that it needs to keep my sequence value around in memory until all the lambdas run, but when each lambda runs in the separate thread, the reference to the value is pointing at the last value from my for loop. Lambdas, however, have a sneaky little syntax to set the in-loop value instead of the reference. Simply toss on a lambda variable equals loop variable, and suddenly, when the lambda runs, it has the desired loop's value. Next, let's get a little fancy with the code to truly sync up the LEDs with the sound. Wave files are just raw speaker outputs, so I should be able to map the amplitude of the sound wave to the number of LEDs in the LED board that light up. Googling for Python graph wave amplitude gets me to SciPy, which I will use, and a MATLAB plotting library, which I won't. Easy peasy. Now I just need to maintain the separation of the duties of media, which is to read and play the files, and hardware, which is to actually integrate the various sound, light, and screen components. I settled on having sound media use scipy.io.wavefile to pick out the file duration, sample rate, and left and right audio tracks. I then let hardware deal with turning that into a sequence for the LEDs. While I'm in the code, I also cleaned up the LED sequence to run a single thread that sleeps between each step rather than a pile of timer threads that each wait longer and longer time to execute. This should help with the OS managing the threading through the CPU, especially for complex LED sequences that each have a duration of a fraction of a second, but stack up to possibly tens of seconds long animations. Speaking of which, balancing the complexity of the sequence with the evaluation of the wave file's amplitudes was a trade-off. I ended up with a percentage of max that was calculated as an average over a 1/7 of a second, so we get 7 distinct LED states per second. The only real gotcha I ran into there was that at a sample rate of in the 40K range, My sum of samples over number of samples needed for the average overflowed my number primitive. So for now, I just pip installed NumPy to deal with it, but a future version of myself will simplify the code so it won't need such big numbers, which might let me drop the extra dependency. I also used only the left channel data, so a better version might also look for spikes on the right channel too, so the LED board can react appropriately. And finally, I'll likely also want to yield the sequence 1/n of a second at a time, so that longer sound files will immediately get their first LED sequence as Python calculates it, rather than building the entire animation before returning it. With all of those to-dos, let's see where we're at. I had to tweak the ratios at which the LEDs light up, otherwise it's always in green or below range, but I'm going to call this another resounding success. Let's get this onto another ABS perf board, wire up another harness, and boom. For the final assembly, I also wired up a second red LED board as a recording indicator, and an RGB LED for even more UX feedback. This LED has red, green, and blue lights in a small enough area that visually the light mixes to generate the full rainbow of colors. Keen-eyed viewers will notice I switched to a Raspberry Pi 3 version B+. That's because I bricked my Pi 5. My theories are that either 1, because my multimeter uses a 9-volt battery and the GPIO pins work at 3.3 and 5 volts, if I left the harness plugged into the breadboard slots where the GPIO board was, while using the resistance/continuous circuit test on my multimeter, the voltage and current would backflow into the Pi and kill it dead. That, or while I was unplugging from the Rodom touchscreen plus speaker combo to use the small waveshare monitor with my own amp and speakers instead, I could have static shocked the assembly and blew out my EEPROM, which would also kill it dead. Either way, be careful with electricity, folks. It's not just you that'll get fried. So anyway, I have another Pi 5, but a Pi 3 was easy to get a hold of and easy to replace. Also, I don't need the Pi 5 only Halo AI module or 12 megapixel camera for this video, so my cautious side, aka cheap side, won out, until I finalize my circuits and print a case to protect everything anyways. Now to the demo. The RGB LED is on in cyan mode when app.py is running and in standby. It switches to orange mode, aka thinking, when I press start, and also turns on the red indicator LED. Right now the animation is hard-coded to last a few seconds, but will be tied to the computer vision TensorFlow thread eventually. After that thread completes, the camera indicator LED turns off, the RGB goes into pulsing cyan mode, and it plays the selected audio track along with the LED board sequence shown earlier. The mystery for next time is that the monitor immediately disabled the first time I ran app.py. My theories are that either one Pygame took over the video output since the Pi 3 has only one HDMI out, or two, app.py might be using GPIO pins that, when otherwise not in use, would be providing resources like a clock and serial data managers, for example, which it needs for HDMI. Either way, I'll likely be able to get the screen back for the Raspberry Pi OS desktop by running the raspi-config utility on the command line. Future Glenn can deal with that. As we all know, that guy is far more knowledgeable and competent than current Glenn. That's all for now. Here's my design for a camera style case that I'll be working on in the next video. This case will nicely fit all of my electronics, the buttons, sound, and LEDs that we've seen today and in previous videos, as well as the HDMI screen, Halo AI module, 12 megapixel camera, and the battery pack that'll make this whole thing portable. I'll eventually be making a 2-in-1 tablet/laptop case, which is why I had two Pis to begin with, but in my small achievable steps approach to this project, I want to encounter and solve any size constraints and circuitry problems in a simple Polaroid camera style box before I try to miniaturize everything enough to fit into the tablet form factor. The super exciting part, computer vision with the Halo AI module and the 12 megapixel camera, will be in the next video. We'll be getting the HDMI monitor, the text-to-speech generator, and the corresponding app.py software improvements out first. This is Glenn signing off for now. Thank you for watching Try Catch Plan. Bye!